Welcome to lesson 3.2, the side splitter theorem. Now the name will make a lot more sense when I actually explain the theorem to you, but I will say this about today's lesson. The side splitter theorem is a great little theorem that you can use to solve a certain kind of problem. You have to know when to use it, okay, and when you cannot use it. Sometimes you can, sometimes you can't. I'll explain when you can, all right, and when you cannot. So that's the big thing about today's lesson. Know when you can use it and know when you can't use it. So what is the side splitter theorem? Let's get into it, okay? A side splitter theorem. Okay, so a parallel line through a triangle splits the sides of the triangle into proportional pieces. That is the side splitter theorem, okay? So a parallel line through the triangle, in this case, that would be DE to CB. Those are our parallel lines. All right? This line splits the sides of the triangle into proportional pieces. What the hell does that even mean? Okay? Well, what it means is this. This line splits these two sides into proportional pieces. So if DE is parallel to CB, okay, which it is, then we know that the ratio of AD, which is this side right here, to AE, which is this side right here, is the same as the ratio of DC to EB. All right? Now I'm going to say this. We can only use this theorem if this line going through the middle of the triangle is parallel to the base. All right? If it's not parallel, you can't use it. The other condition is that the sides have to be across from each other, okay? So just like you have to be across from each other. It can't be like here. That's not across, okay? It has to be across from each other for this to work, all right? So those are the two big things. If they're parallel and they go across, then you can use the side splitter theorem. Let's take a look at how we can use this. In triangle PQT with RS parallel to PT, all right, so our line through the middle is parallel to our base. We're looking good so far. What is the length of ST? So ST is right here. Let's put an X there like we did last time. Now we can use the side splitter theorem. Why? We have the parallel bases, and if you look, these numbers are across from each other. Okay? So let's set up a ratio. The ratio is this. We know that QR to QS, all right? I'll write that out first. QR to QS, right? QR to QS is the same as RP to ST. RP to ST. Pause the video if I'm going too fast and you can see what I'm talking about. QR to QS and RP to ST. So let's just replace the numbers that we have for those. So QR is 4, QS is 5, 4 to 5, and that's the same as the proportion of 8 to X, RP to ST. To solve this, we can just cross multiply. We get 4x is equal to 40. And divide by 4 on both sides. And we get x is equal to 10. Okay, so to answer our question fully, ST, the length of XC, is 10. Now just to make a little more sense of this, all right, 4 is to 5 is the same thing as 8 is to 10, right? That is our good proportion. That's double the proportion. So yeah, that's how you use it. It's just always across from each other. See how easier that makes that? Now for this one, let's try this guy. In the diagram below of ABC, we know that BA, which is this line right here, is parallel to ED. All right, so this line in the middle is parallel to the base. All right, we got the parallel. Now we know that AE is 14. AC, which is this whole thing, is 21, and BD is 6. Find the length of CD, which is right here. All right, so far we're looking good, right? We have the parallel bases, and then we almost have numbers across from each other. We have 14 and 6, which are across from each other. But we don't have a number for CE, because this needs to be across here. But we can actually figure that out, right? If we know the whole length of CA is 21, and we know that EA, this length right here, is 14, I could just subtract 21 minus 14, right? The whole thing minus this piece to get 7. So CE is 7. So now we're set up. I have the numbers that are across from each other, right? And I have the parallel bases, right? The line in the middle parallel to the base. Well, now we can set up a proportion. The proportion would look like this. CE to CD, right? CE to CD is proportional to EA to DB. Once again, pause the video if you're like, whoa, he's going too fast. That's what the pause button's for. Now let's just replace these sides with their side lengths. So we have 7 is to x. All right, 7 is to x as 14 is to 6. Now just to tell you, I've seen people mess this up. Always start on the same side with your proportions. See how 7 and 14 are on top? That's from the same side of this triangle. Okay, now you just cross multiply. 7 times 6 is 42. X times 14 is 14x. If we divide both sides by 14, we get x is equal to 3. So CD is also equal to 3, right? Because that's what we labeled. You got to answer the question. It's not x. We made that up. CD is equal to 3. Awesome. All right, here's our last example, okay? In the triangle below, JK is parallel to YZ. Looking good. We got the parallel. XY, this whole length right here, is 18. XJ is 4. And JK is 10. Now, I'm going to say this. Just as before, we need to find what this part is, right? We know if this is 4, what is this? Well, we could do the same thing as we did before. We could subtract 18 by 4. That's the whole thing by this top part. So let's do 18 minus 4. And we get 14. So we got 14 right here. Okay? Now the question says, what is YZ? Which is right here. So that's where our x goes. Now, even though the bases are parallel, we got one check on this condition. If you look here, there's nothing across from these numbers, right? They're not across. So this is not a time where we're going to use the side splitter theorem, all right? Because it's not across. That has to be the side splitter theorem. It's not splitting the sides. You'll see we're just looking at the bottom part. So I'm being very clear here. Even though it's parallel, they're not across. So watch out. Okay, we are not going to use a side splitter. And that's the big thing with this lesson. You have to know when to use it and when not to use it. And when you don't have any numbers across from each other, then you can't use it. So we're going to have to use the technique we used in the last lesson, which is if we have two triangles that are within each other, then we're going to have to draw two triangles. So we have our smaller triangle right here. And I'm telling you, you got to draw the two triangles to do these. So our smaller triangle has sides of, well, let's see, that's x, j, k. That's our smaller triangle. And our bigger triangle is x, y, z. Okay? Our smaller triangle has sides of 4 and 10. Our bigger triangle has sides of 18, right? That's x, y, and y, z is x. Now we'll set up our ratio and solve this one, all right, which is different than the side splitter. So we'll set it up. The corresponding sides are xj and xy, so we'll say 4 is to 18 as 10 is to x. Okay? We're going to cross multiply. We get 4x is equal to 180. Okay? Divide both sides by 4. And we get x is equal to, let's see, that is 45. Boom, boom, bing, bang. Okay? So to answer our question, yz is equal to 45. So what you should have learned from this lesson is, just to review, if you have a line through the middle that's parallel to the base and numbers across from each other, all right, then the sides are split into proportional pieces, and you got this nifty little theorem to help you out. But if they're not across from each other, you got to do it the old-fashioned way and split up those damn triangles. Aight? All right, that's it for this lesson. Clocking in under 10 minutes, you're welcome. So as a result, go chill for 3 minutes. You're good. You're good. You good.